My name is Michel Lang from INRAE, the French National Research Institute from Agriculture, Food and Environment. I will start my presentation on flood frequency analysis using historical data. Then I will present 3 case studies on the Rhône, Rhine and Garonne rivers in France and Germany. And I will conclude on the benefits and limitations of historical flood information. Flood frequency analysis is based on extreme value theory, which states that the maximum of any random variable converges in probability to the GEV distribution, assuming that the sample of maximum values is IID with independent and identically distributed values. The GEV distribution has 3 parameters, and according to the value of the shape parameter Xi, we have a variable, a Gumbel, or a threshold distribution. But as the IID assumptions are never totally agreed, and as the size of the annual maximum values is not very large, a few decades, we have very large uncertainties when estimating extreme floods from a short series. Hydrologists proposed several methods to improve the estimation of extreme floods. It is possible to increase the sample size by adding information on historical floods or by gathering flood information at a regional scale. It's also possible to simulate long series of rainfall events and convert rainfall into discharge using a hydrological model. I will focus here my presentation on 3 case studies with historical flood data. Here you can see some examples of historical flood information. It can be based on flood marks or documentary sources. Usually, historical flood information is related to flood level. Then we have to convert flood level to flood discharge using hydraulic information. We use the Baratta method, which with a Bayesian combination on hydraulic prior and gauging information. At the end, we have an estimation of the rating curve, the relationship between water level and water discharge, and a credibility interval. Here we have an example of a short series in green between 1950 and 2020. At the right, we can see that the models 1 and 2 give similar results on small return periods and have very different extrapolations for large return periods. And now, if we add historical data in blue, we can see that in some cases it can help us for estimating extreme floods, where extrapolation number 2 seems more likely. Estimation of the parameters of the flood distribution is usually based on the likelihood method. It is possible to write the likelihood function of a big sample with annual maximum values during a modern period with continuous data on a set of historical flood larger than a perception threshold. So now we will see the first case study on the Rhône River, the larger basin in France. The previous study in 2000 did not use all the available data. After a specific inventory work, it was possible to extend the size of the series from 100 to 150 years. We added 450 years of record on a set of 10 stations. The longest series is located downstream at Beaucaire since 1816. You can see on the graph on the x-axis the year, on the y-axis the relative uncertainty on annual maximum discharge. Accuracy is very good during the modern period, about 5%, and it's larger at the beginning of the 19th century, about 30%. If now we estimate the Q1000 flood from a short series from 1971 to 2016, we can see we have very different estimations using a Gumbel distribution on the left or a GEV distribution on the right. the GeV distribution was discarded as the uncertainties are too large, about 150%. If we use a long series from 1816 to 2016, we can see that the Gumbel distribution is not adequate according to the experimental distribution. It's better to use the GeV distribution, which has acceptable uncertainties less than 50%. At the end, we have a downward revision of extreme flood with long. Now, the second case study is related to the Upper Rhine, which is the borderline between France and Germany. There was a large controversy on extreme floods. The Q1000 flood, as estimated by the Germans, is considered to have only a 100-year return period by the French. In fact, as there was large river works on the Rhine rivers during the 19th century, Germans consider such old information was not adequate. They prefer no use of historical floods, as the French use 6 historical floods since 1802, but without any flood correction. At Basel in Switzerland, at the upper part of the Upper Rhine, we have flood data since 1808. It's one of the longest continuous series of discharge in Europe. There was also very interesting work by Vetter in 2011, who did an inventory of historical floods in Old Basel since 1225. Now we test the consistency of the historical flood series with a Poisson test. On the graph at the bottom on the left, we have on x-axis the year, on y-axis the cumulative number of floods since the starting period. If the process is homogeneous, we should have in blue an experimental curve near a straight line. We can see here that the experimental curve in blue falls outside the 90% confidence interval. It's the same with the second graph in the middle part. So the conclusion here is that we have a problem of heterogeneity with historical. And it can be explained by the fact that there were large hydraulic works on the High Rhine. In 1714, there was a derivation of a tributary of the Aar River into Lake Thun. After this derivation, the flood lamination effect is estimated about 270 cubics. At the end of the 19th century, there were also water correction works in the Jura with a lamination effect between 0 and 600 cubics according to peak flood. So we use now corrected series, taking into account that old floods would have today lower peak flood according to the hydraulic works. And now we can see on the 3 graphs at the bottom that the series can be considered as homogeneous, starting from 1225, 1714, or 1808. And we have now reported on the graph the uncertainty and flood discharge according to the year. As with the first case study, we see that historical discharge estimates have larger uncertainties compared with modern floods. Now we will use as a reference a 2-century series from 1808 to 1217. We will compare the flood distribution using only a series of 1 century since 1919, or adding 7 historical floods during the 19th century. We can see that using only 1 century gives an underestimation of flood control, but adding 7 non-historical floods gives no bias and a reduction of uncertainty. Here we compare different floods, Q10, Q100 and Q1000 discharges. In orange, using 1 century, in yellow using 2 centuries, in green using 3 centuries, and in blue using 8 centuries. And we have very similar estimates using 1 or 2 centuries. The set of historical floods contributes to an increase of flood quantities, but uncertainty on extreme floods remains unchanged. So let's move to the third case study on the Garonne River near Agen. It's related to the safety of nuclear power plant based on Q1000 plus flood, which is the upper bound of the 70% confidence interval of the Q1000 flood, plus a safety factor of plus 15%. In fact, the design flood is very sensitive to the choice of a distribution, a Gumbel or GeV distribution, and to the choice of the dataset, using a heterogeneous series from 1915 to 2012, or a part of this series since 1956. Q1000 plus is estimated between 12,500 QMax and 16,000 QMax. So there was an additional study in 2022 adding historical information since 1435 and using a flood frequency model accounting for discharge uncertainty. We collect data from 3 gauging stations near Agen. In blue, the La Magister series with a lot of information since 1967. In green, the Mallows series, an older station which was stopped in 1966. And in red, the Agen series with both annual maximum floods since 1852 and historical data since 1435. According to different plan view, the Cassini map at the end of the 18th century, public works or military maps in the 19th century, or modern maps today, we don't see any major morphological changes. Using different longitudinal profiles, for example in 1858 or today, we see some morphological variations in the altitude of the bed river. But near the Agen Bridge, where the bed is solid with rocks, we don't have morphological changes. So then, using information on gauging and survey of the bed river, we were able to re-estimate flood discharge. At La Magister, we have some upward revision on the first period from 1967 to 1992. At Mallows, we have a downward revision, and at Agen, we have a slight downward revision. The last graph gives the flood discharge uncertainties about 3 to 4% on the modern period and about 28 to 35% on the historical period. So now we check the coherency between our flood series in blue, Mallows plus La Magister, and another series upstream near Toulouse at Portet-sur-Garonne. On the top, we have the 2-time series. On the middle, we fit a regression between the 2 series. And at the bottom, we apply the Bois test on x-axis the year, on y-axis the cumulative regression residuals. The 2 series are considered as non-coherent, where the experimental curve in blue falls outside the 95 confidence interval. And now we apply the same test, but with the corrected series Mallows-La Magister. We can see that the corrected series is now considered as coherent with the Portet-sur-Garonne series. Here we compare the estimation of the Q1000 plus flood in orange using a Gumbel distribution on a heterogeneous series, in red using a GeV distribution on a small homogeneous series, and in green using a GeV distribution with corrected series on historical data since 1413. We have an estimate of about 11,200 QMax, which is near the design flood estimated in 2000. The conclusion was that there was no need to reinforce the protection of the nuclear power plant. So now some conclusions on the 3 case studies. On the Rhone River, adding historical data since 15,000 and with longer discharge series, it was possible to reduce the uncertainties and the design values were revised downward. On the Rhine River, instead of a binary choice, not using historical data or using historical data without data review, we apply a statistical framework accounting for uncertainties. It was possible to obtain a final agreement between the 2 countries. On the Garonne River, there was some opposite studies on the safety of industrial plants. Investigation and review of historical data allow taking a final decision. Now I finish by a general conclusion. Historical information may or may not enable better estimation on extreme flood because we have 2 opposite effects. The sampling uncertainty is reduced as the length of the series increases, but we include less accurate data on the historical period. So it's important using an adapted probabilistic model using a mixed sample on accounting for discharge uncertainties. A specific work is necessary to enhance the value of archive sources with inventory work, digitization and data review, and reconstruction of discharges with uncertainties. And the next challenge will be to reconcile historical data and future flood risk with climate change. Thank you for your attention.